Welcome to Ask and Learn.
All right, we're going to be doing problem 126 of chapter 5 in Chemistry Central Science. So we're going to be looking at a methane molecule. So we're going to be imagining the CH bonds are extended to infinity. So it'll be functionally as if methane gas is producing in gaseous carbon and gaseous hydrogen. Well, gaseous hydrogen atoms. Compare this process to the reverse process to produce the standard enthalpy of formation of CH4 or gas. So we have our process where we're expanding the bonds, and we have our process where we're showing the decomposition of methane into carbon and hydrogen. You can see that in this case we're forming solid carbon and we're forming H2 gas. So now we want to calculate the enthalpy of the change in enthalpy for each case, and want to know which is a more endothermic process. So delta H1 is going to equal, remember Hess's law, products minus reactants, 4 times 217.94 minus negative 74.8 delta H1 okay, 4 times 217.94 plus 17.4 minus negative 74.8. That is equal to 1664.96 kilojoules per mole. Now, if we're going to do next delta H, now remember, the delta H of formation for elements in their standard state, that's always going to be 0. So delta H for carbon and H2, those are 0. So the delta H for our product is 0. And we're going to subtract that by negative 74.8 kilojoules. So delta H is equal to positive 74.8 kilojoules. So, and you'll see that the delta H for the expansion of our molecule is higher than the delta H for the decomposition of our molecule. And the reason for that is that when you convert gaseous carbon into solid carbon, that's an exothermic reaction. And if you were to include that reaction, that would drop down the delta H value you see in H1, that would drop it down to the delta H value you see in H2. But we're not seeing that kind. But because that we're just expanding our molecule, we're not causing that phase transition. We don't have that large negative delta H, so that's why our delta H value is so positive in this case. Now, we have two masses. The mass of our CH4 is equal to 3.45 grams, and our mass of F2 is 1.22 grams. So they want us to figure out what's the limiting reagent in this reaction. So we're going to do this. So 3.45 grams times 1 mole over the mass of CH4, which is 16. We're going to multiply the 1-to-1 ratio for CF4. Or so then we have 88 grams per mole. And then we're going to put 1.22 grams divided by 1 mole, divided by 38 grams per mole times 1 over 4 times 88 grams per mole. So our two answers are going to be 3.45 divided by 16 times 88. We have 18.81 joules. Sorry, 18.81 grams. At 1.22 divided by 38 divided by 4 times 88. That's going to be equal to 0.7, let's say 71 grams. So now they want us to know how much heat was evolved during this process. So we can see that our limiting reagent is going to be our F, then our F2. Let me just circle that. Or rather, let me just write down F2 is limiting. Now, the way to figure out how much heat evolved from this, we have to find out how many, we're going to use these ratios to figure out how much of our CH4 was involved in the reaction. So we're going to do 1.22 both times 1 over 38 times the molar ratio 1 over 4, 1 F2 over 4 fluorine, 1 CH4 over 2 F2. That's going to give us the moles of CH4 that reacted. Zero 0.008 moles. Now we're going to multiply this by our delta H value, which we got over here. Sorry, not the delta H value we got over there. First, we're going to calculate the delta H value, and then we are going our standard delta H value, and then we're going to use it. As remember, Hess's law, delta H of reaction is equal to delta H of products minus delta H of reactants. So we're going to have, in fact, it might be easier if we just go to a new page. So delta H is equal to 2. It's equal to 4 times 286 to 268, 8.6 minus 679.9 minus Remember, this is fluorine in standard state, so it's delta H is 0. So we're going to get the delta H of CH4, so minus 74.8. So delta H that's going to equal negative 1679.5 kilojoules per mole. So then we're going to multiply the moles of CH4 we have here that reacted. So we're going to multiply 0.08 as 0.22. So minus 1679.5 kilojoules per mole times 0.008 moles is going to equal us minus 13.44 kilojoules. So that means Q is equal to minus 13.44 kilojoules.